Hey, so in today's lesson, we're going to understand a little bit more about quantum gates and how they behave. First of all, we gotta start by saying what a state is. In this case, we're seeing a cat. This here is a cat, and also if he had the conjugate, it will be a bra. So in those two matching are a bracket when you have the other part. So let me just write it so you to understand a little bit. Something like this. This is the bra and this is the cat, and both become a bracket. So that's the famous bracket, and this is Dirac notation. Which the cat means is just an state, and the state also means a vector, so you don't have to struggle a lot with that. It's you just have to think like a vector. Um, Okay, so by understanding that, we can go and start seeing what gates are. Our classical gates that we already know are the AND, NAND, OR, NOR, and a lot of those, right? So these are commonly used in electric circuits as part of the engineering and all that stuff, and they are usually seen as this, but what all they are is just binary operations. So AND means that if you have one and one, your output is one, and also what else? Not it negates your operation. So if you have one or true, it will become false, and that's it. I must think that you have some knowledge about this because it is pretty straightforward, and well, it is what in school they teach a lot, right? Uh, okay, if you don't, you can check it out, but it's not very important because we'll see that quantum gates are a little bit different. So in our case, what interests us is more about the classical part. I mean the quantum part. Okay, in quantum, as we saw, states are more like vectors, and operations here, where let me just write something. You usually have some operation like this in quantum, which is okay. Let me phrase this. Okay, which this is a Hamiltonian of this state, which is the the energy of the state. Um, okay, so you can represent your operations by with matrix, such as let's see the identity matrix, which is the most let's say basic one, because what it basically does is just keeps the state as it is. It doesn't do anything at all, basically. Let's see here, we have the identity gate, and when you apply the identity gate to a zero qubit, a zero state qubit, you have the output also in zero, and one becomes one also. So it's just not doing anything, but it is also good to see it as a matrix because you're seeing visually, right? Um, Another gate that is very important in the quantum area are the Pauli gates, uh, which they can be X, Y, or Z. But in this case, we have X right here, which is may also not. And what it does, basically, it negates it is like a not gate from classical, which is negating so the state. So if you have zero, your output is gonna be one, one, it's gonna be zero. Very very straightforward. So you shouldn't have a lot of trouble understanding that. Also, Hadamard is very important gate because it enables you to convert your qubit into a superposition of states. The most common one is this one, where you have a 1 divided square root of 2 of 0 and plus 1. And also, yeah, so another gates that we're gonna see a lot is the control the C NOT gate, which is control NOT. And what this does is basically it takes a qubit, let's say right here. uh, this is the controlling one qubit, and this is the controlled qubit. So this dot means that this qubit is controlling this. So if you have one and then apply a Hadamard, it's gonna control how it's gonna behave this state. So in order to be okay, let me see. Okay, so this C note, it means that if this the C NOT gate, it means that if you're what it is basically means that it is entangling the two qubits, but also it's saying that if your qubit is initialized, the control qubit, which is the one with this dot, this is the control. I mean, this is the control qubit, and this is the control qubit. So basically, if this is initialized, or it is in one state. So let's say here we have it in one state. It's gonna become 1 to 1 because it's negating this. Also in this part, you can see we have one, and it's gonna negate the other qubit. So it becomes 1 0. As in comparison to these ones that are both on 0, it doesn't happen anything because of that. And lastly, we have the Toffoli, which is doing the Toffoli is kind of a C node, but you have to aggregate another control qubit. So you gotta have the two first qubits, or at least the control ones, in a one state. So in order to negate the last qubit, which is this, and as you can see, we have 1 1, and then negates the 0, and it becomes 1. And the other parts, in the other states, it doesn't, because we have 0 0 0 1. We have all these 1 0 here, the same. It keeps the same state. Just in these last two states, it negates the last qubit. So those are the most important gates right now in quantum computing. Just we have a circuit right here, so you can see how the gates are implemented. Right here we have a CNOT gate, then we have a Pauli X, then in the second qubit we have a Hadamard, a swap, a Pauli Y, also Toffoli, a Pauli C, and this all in combined makes a algorithm that's gonna enable us to applicate something that we want, right? So something that I didn't mention, and it's very important, is this. It's not like a gate, it's more like, I don't know if it's a gate, but I would say it's just measurement. And what is important to, well, in classic computer, when you measure something, you are not modifying anything. But in quantum computing, when you measuring something, you can see it in the double slit experiment, the famous one where you have electrons going through two slits. And when you measure a particle, you basically collapse their state. So this, you can see it's something like, okay, so yeah, in the slit experiment, when the electron is measured at the slit, it collapses their wave function, and it goes just one direction, right? So what's basically happening here is that you measure this, and I mean, this qubit is not entangled with any other qubits, and it doesn't have a gate, so it doesn't really. When you're measuring something, you gotta keep on account that something might modify something else, because let's see, Okay, when you have a state something like this, you got it, right? So the probability of measuring 0 and 1 is 50-50 each, 50% each. And also if you measure, like, let's say here, this qubit, and this qubit will was in the zero state. I mean, you're gonna measure here 0 because no gate was applied. But yeah, let's say that you have this state. So if you get a measure here, you have your, maybe if you have this state because you apply some gates, and then you wanna do something with this state, uh, it wouldn't be okay if you measure right here, because then you'll get your qubit in either one of these states, and you have to apply all the gates once again, and that's not like where you're seeking, right? So yes, you just gotta think that measuring is something very important, and by measuring you are modifying the structure of the circuit. It's not like just the end of the circuit. You can measure something and then continue applying more gates. So that was all for this video. I hope this was helpful for you guys, and I'll see you on the next one.